Hello, calculus family. Today we are going to talk about absolute extrema. Depending on when you're watching this video, you may have already heard about absolute extrema or relative extrema or local extrema, but we're going to go through and talk about how do you find the absolutely highest point or the absolutely lowest point on a graph across either a given interval or across its entire domain. So, absolute extrema are really a consequence of what's called the extreme value theorem. And the extreme value theorem says that if f of x is continuous on the closed interval from a to b, then f has both a maximum and a minimum on that interval. Now, there are a couple things that I want to highlight here. Number one is this only is true if you have a continuous function on a closed interval. If you have a function that is not continuous, then it is not guaranteed that you have that highest or a lowest point. Okay, so it has to be continuous on a closed interval. If you have it on an open interval, same thing, there may not be a highest and or a lowest point because you may have arrows or holes or things like that. All right, so things that I just said out loud that we're going to write down is continuity must exist. You have to know it's continuous, and you have to know that it's continuous on a closed interval. Now, if something isn't continuous or isn't closed, it might still have a highest or a lowest point, but it's not guaranteed. Another thing that we're going to talk about here is when we talk about extreme values or absolute extreme values, we are often talking about extreme values, not just the x value where it occurs, but the y value. So if I say find the absolute maximum value of a function and I just say value instead of x value, what I mean is I want the y value. So long story short, if you are ever identifying absolute max or min, I want to know what the y value is at those places. If you are interested in any possible extreme values on an open interval, there may be 2, 1, or 0 extreme values. That's that idea that it's just not guaranteed anymore. So sketch a graph of a function on a closed interval where the absolute extrema occur. Okay, how about at a peak and a valley? So I could have something like this, where my absolute extreme values, okay, there's a closed interval from a to b, and up here would be my absolute maximum, and down here would be my absolute minimum, because that's the highest y value and the lowest y value I get to. These also happen to be relative extreme values. That's a local max and a local min. Now, I could also have a closed interval where my absolute max and absolute min occur at endpoints, so I could have something that maybe looks like this. And my absolute max is at that endpoint, and my absolute min is at this other endpoint. But I also have relative extreme values in between. I have a local max and a local min. I said that backwards, but you know what I mean. At those two values as well. And then I could have one of each. I could have it occur at a peak or a valley and an endpoint. So I could say, here's my absolute max, but my absolute min is down here. So this is both an absolute and a local max, and this is an absolute min. Okay. So long story short, these absolute extreme values can be critical values or they could be endpoints. Now, I drew smooth curves, but there was no rule in the extreme values theorem that said f of x had to be continuous and differentiable. It doesn't have to be differentiable. So you could have absolute extreme values that occur at points like this, and that right there is both an absolute and a relative max. And this can be an absolute and a relative min as well. And my endpoints are nothing. And then last but not least, technically, if I had just y equals 6, my absolute max and my absolute min are both the same y value, which is 6. The highest point it gets to is 6. The lowest point it gets to is 6. Okay, and then what about if you have open intervals, but you're still interested in absolute extrema, which is fine. You could have something where there's only an absolute maximum. One example of that would be this. Okay, that's an open interval because it goes from negative to infinity, but it's got an absolute max. I can also have an open interval where there is an absolute max and an absolute min, And that could be something like this. Because that's an open interval. I still have a highest point and a lowest point. That's okay. And then I can have an open interval where there's neither an absolute max nor an absolute min. And an example of that would be something like this, where I don't have an absolute min because it keeps going down. And over here on the left, I don't have an absolute max because technically this keeps increasing. It never makes it to that value, but it keeps technically increasing and never makes it to a highest point. Okay, it has like an asymptotic increase in y, even though there's no asymptote. The y values are just never going to approach, let's say like this is 4. Those y values are never going to approach 4. They're going to keep getting closer, 3.9, 3.99, 3.9999999, never going to get to 4. All right, so things you need to know on a closed interval. Absolute extrema can occur at one of two places. They can occur at endpoints, or they can occur at critical points. And my automatic lights turned off, which is why it looks like I'm in a horror film. Ha ha, let there be light. So endpoints are critical points, and a reminder, critical points are where your derivative equals 0 or dne. All right. Oh, look at that. I even had it in a box below. I didn't need to write it there, but it's worth writing it twice. X equals c is a critical point of f if f prime of c equals 0 or if f prime of c doesn't exist. Sometimes I just know too much what I'm going to say. All right, so steps for calculating absolute max and min values. I'm not going to read the steps. I'm just going to do the steps. These are here for you to reference back before. All right. Find the maximum and minimum values of this. So here are the things that you need to consider, which is why I wrote the steps before. If I want the absolute max and minimum values, I need to consider endpoints and critical points. So what I'm going to do over here is I'm going to call this my test table, or my potential values. And over here on the left, I'm going to put all my potential x's, and then I'm going to find the y value for each of those x's. So I'm immediately going to make a testing table over to the left. And if I want to know my absolute max and min values on -6 to 6, I know I need to test -6 and 6 because those might be my absolute max or min coordinates, all right? Well, I've already considered my endpoints. Now I need to consider my critical points. To do that, I need to take the derivative. So f prime is going to be 3x squared minus 12x minus 15. And I want to figure out when that equals 0 or doesn't exist. This is a quadratic, so it always exists. Want to figure out when it equals 0, so I'm going to divide everything by 3. X minus 5, x plus 1. So I get 5 and -1 are my critical values. Okay, here's the thing. If I were looking for relative extreme values, the next thing I would do here is make intervals and figure out when f is increasing and decreasing and try to find a relative max or relative min and whatnot. I don't need to know any relative values. When you want an absolute extreme value, you really just want what is the absolute highest y value you get to and the absolute lowest y value that you get to. I don't need the intervals to do that. All I need are the y values that I'm going to put right here. And then I'm just going to compare them. Okay, so now I'm just going to find f of -6. Oh my goodness, this is going to take me a while here. So I'm going to be a little bit lazy and use a calculator here. So I apologize that you have to watch me pull this up. The calculator I want to use on my computer just doesn't work. All right, so Desmos, here we go. And actually, what you can do is even do this in the graphing calculator. So things I'm going to teach you here is we had the function f of x is x equals x cubed minus 6x squared minus 15x plus 10, okay? And I'm graphing this from -6 to 6. So if I want to look at it, I can actually see it right here. Whoa. Okay, so I can kind of see it right here. And it looks like my absolute min is going to be on the left endpoint, and my absolute max is going to be at one of my critical points. Okay, so now that I can see it, that's a little bit helpful. And now I just want to evaluate this at -6, 6, 5, and 1. So f of -6 is -332. Let me write that down, -332. F of 6 is -80. F of 5 is -90. And f of, what was the last one? -1 is 18. Okay. So now I know that this is my absolute minimum value. And I know that this is my absolute maximum value. Okay. So when you find absolute extrema, make a test table, input your endpoints, take the derivative and set it equal to 0 or DNE, find those x values, put them into the table, and then find all your y values and see which one is the highest and which is the lowest. And that's what I got. Okay. Let's do it again. Find the absolute extreme values of this function on the interval from -5 to 5. Okay, fine. X, f of x, -5 and 5 are my endpoints, so they have to go in my test table. I'm going to take the derivative 2/3 x to the -1/3, and I'm going to set that equal to 0 or DNE, and that's really 2/3 times the cube root of x, if you want to think of it that way. Well, my numerator can't equal 0, so this can never equal 0, and it won't exist when x equals 0. So I have one more critical point. All right, so then I need to find the y values at -5, 5, and 0. X to the 2/3 plus 4. X to the 2/3 plus 4 on -5 to 5. Okay, I can probably zoom in more and kind of look at this one. I can't find it. There it is. Oh, it looks like a little seagull. And we wanted to evaluate this at the end point. So at -5, it's 6.924. At the other value, that's also going to be 6.924. And at x equals 0, I get 4. This example is on here because you might be thinking, wait, there's two absolute maximums. There's two locations where the absolute maximum value occurs, but there's one absolute maximum value. So 6.924 is the absolute max value, and 4 is the absolute minimum value. Okay. Find the absolute extreme values of f of x on 6 minus x squared on the interval from -2 to 3, but it's open at the end point. Okay, so now I really need to think about this one, and what do we want to do here? So what I'm going to do is I'm still going to make one of these test tables. And -2 I'm going to put here. And 3 I'm going to put here, but I'm going to put a hole around it to remind myself that it doesn't really exist. I'm just using it to figure out, is that going to be a place that I really care about? Okay, and I'll explain that in a minute. Okay, so I think about that, and then I need to test my critical point. So f prime of x is going to be -2x. That equals 0 DNE. It's going to equal 0 at x equals 0. It always exists. All right, so if I plug -2 in for x, I don't really need a calculator for that. That's going to be 6 minus 4 is 2. If I plug in 3 for that, 6 minus 9 is going to be -3. And if I plug in 0 for that, I'm going to get 6. So what I'm realizing is that this is my absolute maximum value. This really wants to be the absolute min, but that's a hole, so there is no absolute min value on this open interval, which is fine because I guaranteed a max and a min on a closed interval. I'm not guaranteed a max and a min on an open interval. All right, and then number 4, find the extreme values of f of x on its entire domain. Okay, so what's the domain of this? The domain is that 1 minus x squared needs to be greater than but not equal to 0. And the way I'm going to think of that one is I'm going to say, well, you know what? 1 minus x squared looks like this. It's greater than 0 between the roots. So my domain is -1 to 1, non-inclusive. So I'm going to do my test values, x and f of x, and I'm going to test from -1 to 1. But again, these are actually open, okay, because I can't include -1 and 1. And then I need to find my critical values. Fine. I need to take the derivative. You know what? Before I take the derivative, I'm going to think of this as 1 minus x squared to the -1/2. So then f prime is going to be -1/2 1 minus x squared to the -3/2 times -2x because of the chain rule. So I really have, let's see, those will cancel, positive there. So I have x over 1 minus x squared to the 3/2. I want to know when that equals 0 or doesn't exist. It equals 0 at x equals 0. It doesn't exist at x equals plus or minus 1, but I've already used those, so I can ignore them. So I just need to add 0 over here. One thing that hasn't come up yet, and I wish it did, but I just didn't pick the right examples, is you always want to consider whether the points you get here are actually on your interval. Like if I got a critical value at 6, and 6 isn't on my interval between the endpoints, then you just wouldn't test it. Okay, but 0 is between -1 and 1, so I do want to test it. And then I want to plug these into the original. So at -1, well, this doesn't exist. At +1, my function doesn't exist. And at 0, my function equals 1. Well, how do I know if 1 is a max, a min, or neither? Now we need to do some thinking here. We need to think about some limits. So right here, I want to think about the limit as x approaches -1 for 1 over the square root of 1 minus x squared. Well, as x approaches -1, my denominator is approaching 0, right? Because I'm taking the square root of 1 minus 1. My denominator is approaching 0. When I square root something, the result is going to be positive when it's not 0. So I have +1 divided by an infinitesimally small positive number. So 1 divided by an itty-bitty positive is really going to tend toward infinity. And if I throw a +1 in there, the same thing is going to happen. So the graph of this function towards those endpoints of the domain goes up, which means this is an absolute min. Okay, and if you don't believe me, 1 over the square root of 1 minus x squared looks like that. So those are all my absolute extreme values. I just wanted to make sure I didn't miss an example there. And that's how you do it. So I hope everybody is having a good day. Really terrible joke of the day. I haven't done a joke in a while when I've made my videos. Really terrible joke of the day is, what do you call a cow with no legs? Ground beef. And just to make it a little bit more lighthearted, what do you call an elephant that's wearing a tutu, slippers, and a Superman mask? I guess it would be a Spider-Man mask. Superman doesn't wear a mask. So let me change that joke. What do you call an elephant that's wearing a tutu, a Spider-Man mask, slippers, and earmuffs? That's what that joke is supposed to be. What do you call an elephant wearing earmuffs, a Spider-Man mask, a tutu, and slippers? Doesn't matter what you call him. He's not going to hear you because he's got earmuffs on. I know. I'll stop now. Have a great day.